So now the previous lecture we talked about filtering in the frequency domain, but now we are going to talk about how the filters operate. You can see here that we have the high pass filter. This is the ideal high pass filter. This is the Butterworth high pass filter, and this is the Gaussian high pass filter like we discussed earlier in the previous lecture. We have these equations. This is for the ideal, this is for the Butterworth, and this is for the Gaussian. And you can see that the difference in the equations compared to these equations. This is the Gaussian low pass filter. It was e to the power minus d square uv over 2d square. So the here the Gaussian will be 1 minus, okay, it is 1 minus the value. Now you can see that the high pass filters, as they operate in the spatial domain representation, and this is the frequency domain representation. And applying a ideal high pass filter for an image, as you can see, it changes the values of an image. So the high pass filter of the image, remember, it always makes the image darker, because we will remove the low frequency values. The low frequency values, they hold the original value, which is the average value at the center of the image. So the results of D 15, 30, and 80, as you can see, as more you go to the higher frequencies, you lose some lightness, but you gain more information. So this is the Butterworth high pass filter. It becomes more and more. See here how the ripples are appearing in the image. Here they are disappearing, but in the Butterworth there are no ripples from the beginning, but you get better results, as you can see in your image. Here is the Gaussian. The Gaussian is giving even better results as you compare it with the ideal and the Butterworth high pass filters. So this is the Laplacian in the frequency domain. If you remember, and we talked about the Laplacian filters in the spatial domain, and we said this is our filter, which was the Laplacian filter. Now in the frequency domain, the Laplacian filter will look something like this. So applying the Laplacian filter in the frequency domain will give you an image which is something like this. Okay, of course, this is the image after this is the filtered image. Then we multiply the both images, we get this is the output. So implementing some additional properties of the two-dimensional Fourier transform, as you can see over here, we have the images. This is if your center is at 0, 0. Remember, this is 0, 0. So your image will be something like this. These corners are connected together, and the corner from the back. So your image will have these values. So it's better to shift the image by m over 2. Once you shift the image by m over 2, you get the center in the middle. Otherwise, your centers will be in the corners. So here we have the image. Then we do the one-dimensional transform. We get f. Then we do the one-dimensional column transform. We get f of uv. So f of xy, f of xv, x of uv at the end. So here is the convolution once more, and how we apply it to the image, and what is the output of that image. How do we extend the images, as you see over here from the reference book. Some properties of the Fourier transform are implemented over here just to help you if you need them during the class. And this is the end of our module, where we discussed the frequency domain in short, and hopefully we are going to do more examples in the class.